On to empirical formulas now, from percentage to formula. This is where we start working on chemical composition the way true chemists do. We're not going to cut corners like Bart Simpson is attempting to do. We are going to be using our percent compositions. We're going to watch our significant figures because at this point it's going to make a difference in our final answer. And I also wanted to briefly talk with you, and I will talk about it more in class, but where are these in the real world useful to us? Well, anytime you see a company that is selling a chemical, you can bet that there's some other company that is going to try and reverse engineer that and sell it for even cheaper. So it's all about trying to figure out what is the real chemical formula? How many of which atoms are there and in what ratio? That's what makes the chemical. So that's what we're going to be looking at. We're going to be looking at how we do that. Empirical formulas, go ahead and pause the video and write all of this down and we'll go over the examples. But the empirical formula is the lowest whole number ratio of elements in a compound. So I love easy math. Lowest whole number ratio. Yay. It may or may not be the true formula. The two can be the same. They may not be. For example, I know this is an empirical formula because it is the lowest whole number ratio combination of carbon and hydrogen, 1 and 2, 1 to 2. If I'm looking at this formula here, I can further reduce that. If I divide that 2 by 2, that'll give me 1 carbon. If I divide that 4 by 2, that will give me 2 hydrogen right there. So this is the same empirical formula here, but this is a different chemical. This chemical has 2 carbons and 4 hydrogens. So that's what that chemical looks like. And that chemical will react very differently from this one that has 3 carbons and then 6 hydrogens all around it. But if we look at the ratio for this, we can divide each of those by 3 and we're still going to get that same CH2 ratio. So that is our difference between empirical formulas and molecular formulas. And then H2O is an example of which the empirical formula and the molecular formula is the same because that is the way that chemical actually looks. You have 1 oxygen, 2 hydrogens. So that is its empirical formula and its molecular formula. So that's the difference. All right, so let's practice this. Find the lowest whole number ratio. And oh look, she looks just as excited as you are to be studying empirical formulas. So let's find the lowest whole number ratio. Continue this excitement. All right, so I have my 3 elements. What number could I divide each of these subscripts by? Hopefully you said 6. And if you said 2, well then hopefully you would get a lower number that you realize that you could divide even more. So this would be a 1, this would be a 2, then this would be a 1. This would be our empirical formula. And you can have the ones in there in the empirical formula, or if you just want to leave them out like that, that's fine too. This, can we reduce that any more than it's already reduced? No, we can't. Not to have a whole number ratio, and that's what we need to keep, a whole number ratio. Let me give you a couple more. We're going to pause the video, and then, let's just do that one too. Come back and check your answer. Okay, ready? So the first one, that is the empirical formula. Letter B is CH3. Letter C is already in its lowest whole number ratio, so we leave it just the way it is. And then D, we can go to FeCO3. So remember that anything that's in parentheses is protected. So we're going to look at the subscripts that are on the outside. And that's how we would find those empirical formulas. Calculating empirical formulas. To make things easier, we're going to pretend that we have a 100-gram sample, and you see how that makes a huge difference. So then with that, we can change the percent to grams, convert the grams to moles for each element. We're going to divide each number by the least number, And if necessary, you don't always have to do the last step, but if necessary, multiply the results to get rid of any fractions that you have. All right, so pause the video, make sure you have this written down. And now let's put that into practice. All right, so example 1, calculate the empirical formula of a compound composed of 38%, 38.67% carbon, 16.22% hydrogen, and 45.11% nitrogen. So all of this is going to add up to 100%. So to make this easy, let's just assume we have a 100 gram sample. This is percentage. Whatever amount we have, the carbon is always going to be 38.76% of it. So let's just pretend we have 100 grams. And what that means is that our 38.67% carbon becomes 38.67 grams, because out of 100, that's what that would be. All right, so we're assuming 100 grams. So let's do the same for the hydrogen and the nitrogen. Just convert that to grams. Then what we're going to do is we're going to use the molar mass to convert to moles, because that was our next step. So let me use the molar mass for carbon, and I need grams on the bottom. So those will cancel, and I will just have moles in my answer. I'm going to do the same thing for hydrogen and for nitrogen. I'm going to give you a few minutes, calculate that, and then check your answer. Okay? Let's check. When you do this calculation, you should get 3.220 moles. You should get 16.09 moles of hydrogen and 3.219 moles of nitrogen. Right, so this tells us the mole-to-mole ratio that they all relate to each other in this compound. However, these are not nice whole numbers. We need to make them nice whole numbers. And the way that we're going to do that is we're going to take the smallest number. So out of these three, the smallest number is 3.219. So we are going to divide each of these by 3.219 because we want whole numbers. We don't want these decimal numbers. All right, so do that and then show me on the side what you come up with. Pause the video and work that out. Okay, so when you've plugged them all in, you should get a number that is very, very close to 1 for the carbon, very, very close, well, exactly 1 for the nitrogen, and this is going to be very, very close to 5. So the way that you figure out your formula, this tells you you have 1 carbon, 5 hydrogen, 1 nitrogen. So this is your formula. And that's it. That's how you figure out empirical formula. Example 2. Let's pause the video and set this up and then check our answer. Okay, so make sure that you've gotten to this point so far. We are assuming 100 gram samples so that we can easily convert the percentages to grams. From the periodic table, we get molar masses in grams per mole. And again, if you don't like there being naked numbers, or not naked numbers, none of these are naked numbers. They all have units. But if you don't like this area here not having a number, you can put that value over 1. That doesn't change the value, and then it makes sure that all of your places in your long fraction have numbers in them. Okay, so as you calculate these, let's see what your answer is for that. So we should have 1.41 moles for phosphorus and 3.52 moles for oxygen. So which do we have less of? I see phosphorus is the least, so we're going to divide all the numbers by the least number. And what that's going to do is that's going to give us a nice whole number to work with for phosphorus. So this should give us P1. And oxygen, if you divide these, which you should be dividing, 3.52 divided by 1.41, you're going to get either exactly or very, very close to 2.5. This is where the last step, which you don't always have to do, but in this case we do, that last step comes in handy. We cannot have a decimal. We cannot have a fraction of a number. It's got to be a whole number. So the first thing I'm going to do is I'm going to try and multiply both of these numbers by 2. And so that's going to give us P2. 2.5 times 2 is 5. That is a whole number ratio. That is going to be our empirical formula. All right. So if the 2 wouldn't have worked, then you just try multiplying times 3. If that didn't work, multiply times 4. If that didn't work, multiply times 5. But you are usually not going to have to even go up to 5, and you're definitely not going to have to go past that. So that's that example. Let's move on to the third example. All right, so work this, pause the video, and then check your answer. So here we go. Assuming a 100-gram sample, this is the setup that we should have. And again, to make these into fractions, we can just do this. And make sure that on this example, they didn't go to the hundredths place, but if you go to the hundredths place, this is where you're going to start seeing a difference. If you just round this to a whole number, you're not really going to get this number of moles. This is what I calculated. I was able to edit this, and I changed that because when you divide by the smallest number, and the smallest number is the 103, when you divide them all by that, you are going to get much closer to a whole number in your answer than you would have if you had actually used these whole numbers. So for these, you want to use your decimals, 0.01, 0.01. This was 0.01 or 0.08 off the top of my head. I can't remember. I think it's 0.01. This is 0.00. And it seems like it may not make a big difference, but remember that we're multiplying and we're dividing, and so it does. It does make a difference, especially when you're doing so much multiplying across. All right, so you're going to get numbers that are not going to be exact, but the moles of carbon, the moles of hydrogen, what you do get is going to be very, very close to whole numbers. Oxygen will, of course, be 1. So you should be able to come up with this empirical formula right here. And that's how we do empirical formulas. So I also want to, at this point, because it is leaning into what we are doing after this, but the empirical mass would be the molar mass of this formula here. And it's the exact same way that we figured out the molar mass of any other compound. We just take how many elements of each atom is there, and we add up the masses for those. And that's it. So why do we need that? Well, let me tell you. Next slide.